guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now I want to go from the differential rate law to an integrated rate law. And the difference is that we started out with talking about rate versus concentration, right? For the differential rate law. And now we want to convert this to rate versus time. And this is going to be different depending on the overall order of each reaction. And so we're going to start out by talking about first order reactions. And so in a first order reaction, we go from something, let's say A, to B. So this is the reactant and this is the product. And the rate can be written as -1/A, delta A over delta T, which we did before. And this can be written as Ka to the power of N. And since it's a first order reaction, this is just going to be Ka, since this is to the power of 1. But from here, we can actually rewrite this part as the dA over dt, since it's the change in the concentration over a change in the time, and this is Ka. And so this equation is a differential equation that relates the rate of change in a concentration to the concentration itself, which is over here. So the integration of this equation produces the corresponding integrated rate law, which relates the concentration to time. And so you'll need to review a little bit of math to know how to integrate this equation to get ln A equals -kT plus B. From here, the easiest way to integrate this is to separate the variables. So you would go dA over A equals -K dt. And then from here, it's a lot easier to integrate it. And so at a time of 0, the natural log of A, and I'm going to put a 0 right here, which indicates the initial concentration of A at time equals 0, is equal to B, which is the y-intercept right here. And so from here we can get that ln A equals -kT plus ln A naught. And this is now in the form of the equation y equals mx plus b, which is an equation for a linear graph, right? And so I can actually draw it for you right here, where we have concentration versus time. But for the y-axis, to make things easier, it's going to be the natural log of A. And so as you can see, the y-intercept is the natural log of A at time 0, so ln A0, let's say it's right here, and it's going to be a negative slope because of the fact that it's -m. And so it looks something like this, where the slope is -K. And so this is the integrated first order rate law, and it's very useful for doing a lot of calculations. And so a straight line plot of the natural log of a reactant versus time means that the reaction is first order. And this analysis is very useful because it tests if a reaction is first order, and if it is, then the slope is going to be the rate constant.